Yeah. So there's very little code in this talk if you're expecting that. Just usually what I do is I take up a small concept, things that we probably don't associate in our day-to-day coding, but very elementary and essential for us to understand how to write better software. So I've been working in this infrastructure and reliability space for over a decade. And what I've realized is that concepts that I learned long back, and these are things which Unix systems have pretty much from 1970s and 80s. If done right, they're the same principles that we need to do today to write good quality software. So I'll start with a question. There are two servers, 8 gigabytes of RAM, each 55% full. Is this system stable? Or is the system reliable? Yes, no, there's no third option. So, okay. The system is actually not, because come to think of it, just one of them, if it goes down, the load of 55% goes to the other side, makes it 110%. Standard wisdom says, oh, this is going to work. I have two servers, this empty, plenty of space, is going to work, but it won't. It's just waiting for a failure. Another question. Let's say I got 3 servers now, right? What should be the minimum threshold at which I should panic? Should it be 66%? Should it be 75%? What should that number be? Right? Because let's say now one goes down and that load has to spread across to other places. So now this is fine, right? 66%, because you would say that 33 would go out and everything becomes quite stable. Another question. So this is a support ticket that came in a long time back, and somebody realized that on a load balancer on AWS, what was happening was traffic was unevenly distributed across nodes, and this bug was reported a year after the system was deployed and had served around 500 million credit scores. So the question is, how do we detect these things early enough? Are we capable of handling, or is our software capable of handling these problems before it hits us, before a year late we realize that, oh, we're not doing this right? Standard answer, we all say, well, you aren't monitoring your system well. Which raises me to a question. I'm not going to talk about monitoring because, we know, if I ask people what is monitoring, monitoring is what Prometheus does. Monitoring is what Datadog does, right? Any other answer than that? Or maybe what Sensu does, right? The problem with monitoring is, and this is where I'll probably get into the linguistic of things a little. When you are monitoring something, think about it, right? You're already looking for something that you know. As in, when I monitor for RAM failure, I know I am monitoring for something which fails at X%. This is getting into a domain of known failures. It's not going to tell you what is unknown to you, right? What about unknown unknowns? Things that you just don't know. You can't set an alert or a monitor for something that you don't know. This gets slightly tricky. You have to spend some time thinking about this. Right now, when you're looking at a system, right, and you want to monitor it, there is no recipe which says monitor every single use case of this ever possible or every single failure case. You're going to apply monitors and triggers for things that you already know that this can fail in this known manner. So, but that is not going to give you enough to build a system which may fail later. And this is exactly where the concept of observability kicks in. I'm sure a lot of you would have heard this term observability. Has anybody heard that term observability? You have, everybody else have. Okay. What are we missing here? What we are missing is systems are actually distributed in nature as we are growing, right? Now, no longer server is going to run on one single machine. And failures are far beyond what we see as, okay, RAM failure, CPU failure, etc. What about accuracy? What about latency? What about correctness? What about consistency? These are the problems that we usually do not look at a system, right? Standard, like, okay, so I deploy a new login service or a new payment service or a cart service. How do I measure accuracy of it? And as systems move towards more complex paradigms like eventual consistency patterns, right? All of these are known terms. How do we measure that? How do I know whether the response that I'm getting is actually correct or not? You guys know of eventual consistency patterns, right? So I wrote something to a database, I read something from another shard, I didn't get the right value. Is this system correct or incorrect? Is this an acceptable use case for the business or not? So the monitors itself have to get pretty complex as we evolve with the software. So is the consistency pattern about it. Another problem with monitoring is it always tells you a problem till now or from now. So how many of you are aware of kernel traces? Has anybody used a S trace ever? A P trace? These things, right? So, or TCP dump. People are aware of TCP dump? Right. Now, what does a TCP dump do? When you are debugging a network, what you do is you start TCP dump. And it starts showing you something. Like there are certain logs that keep coming out on the screen. Now this is happening because somebody once wrote a software which dumps everything on the TCP stack when there is a monitor applied using TCP dump. This ability to debug was baked into the software. Only then you could later debug it. It doesn't work that way, right? That now you push another build, you're emitting more metrics, you're emitting more log lines, and then you debug it, because the problem has happened. Now you're going to watch a running system. The hooks and levers have to be present into the software. I'll walk you through all of this, don't worry about that. But do you agree with me that the standard way of we say that, hey, we go to Datadog, we go to AWS CloudWatch, we install another alert, and that is enough for us? Probably that's not enough, is what I'm trying to say so far. I'll walk you through a bit of monitoring timeline as well. Like as systems started, earlier we used to monitor servers. When we moved ahead, we started writing complex services as well. We started monitoring services. Late 2000s, we moved towards service-oriented architectures. We had ability to monitor that as well. Early 2010s, there were microservices. Then came Lambdas as nano services, and now there are functionless as well, right? Like all of this falls under the same Lambdas. So whole paradigm of monitoring is also getting pretty complex. The real question, this is what everybody should ask. If a tree fell in a forest and nobody heard it, did it make a sound? Has nobody ever heard this thing? Nobody? Oh, cool. Okay, so anyway, the answer is all falling trees will yield log lines. Cool. Software by design is opaque. To debug and control a running system, you need observability built in. What I'm trying to say here again is, let's say there is, okay, let's make a checkout application, right? Or a payment application. A user comes in, clicks pay now. It's not happening. How do I debug this running system? Why is it not working? Where should I go? What should I look for? Should I look at existing stats which are not enough? Because if they were enough, I would have found something out there. How do I debug this running system? Debugging a running system is almost next to impossible, unless it has emitted every single data point that you would eventually need. This is where tracing comes into the picture as well. When we say request tracing, why do we use request tracing? For the same reason, that tomorrow when something fails, there should be ample data points available for me to debug retrospectively what had failed. Because after something has failed, you can't go back and fix it. I mean, if that was the case, I would have never failed my 10th grade, right? I mean, I could go back and fix things, but I can't. So, if you look at a software, like what are the things that we look at? Things like daily active users. Can you do this without emitting data from within the software? There has to be data points that you need to emit out. There have to be trails, there have to be analytics. Now, are you guys aware of request tracing, distributed tracing? Because this is a point where whoever doesn't understand, just raise your hand and I would want to explain all these things. Do we understand request tracing? Does anybody want me to explain what request tracing is? Okay, good. So, have you guys worked with distributed services, microservices architecture? Okay. Service A calls service B, right? Okay, where do you work? ServiceNow. Okay. Do you have an architecture where there are multiple teams who are maintaining services? Okay. Your API calls another API, calls another API. Now, in this flow of requests, what if something fails? How do we debug what had failed? Now, also on top of this, if I say they were, what language do you code in? Python. Okay. Has anybody coded in Java? Okay, no problem. If you haven't, that's all right. So, let's say there are a million requests coming in. Now, when you look at million log lines and you see there's a million log lines on service A, you see million log lines on service B. No, you can't look at million log lines, right? So, you need to find identifiers, right? You need to know this request in this million is mine. Now, corresponding to this request in this million is what I'm looking for. Now, at that scale, you need correlations where you can trace that a request came in, it went to service A called service B, and this is the same request ID that we're catching and trapping here, goes to service C, so that you can track, okay, if service C did not happen, we are going to isolate our bug. This is request tracing. This is the purpose of it. Does that explain now? Now, this is something that you should be doing if you aren't doing already. You know, like a lot of time you would have heard people emit logs for tomorrow when a failure happens. You know, like usually what we do is we see there's a bug happening, we send another patch which has the log enabled. No, this is not. I mean, this is for tomorrow, not for today. Like today what has failed, you can't still debug it. So the idea is, now there are logs, right? Now, if you look at a standard system, have you, do you guys know of D traces in system, in kernel? So, how do you, okay, now let's say a simple thing, right? Do you have a process which is supposed to call google.com and is not calling google.com? How do you debug this? Any thought? Anybody? Ngrep, that's a good one. Anything else? Does anybody want to give me anything? Would you probably also use a strace for that? Right. You could use a TCP dump as well to see whether it is actually making an outbound connection or not. Now, these are tools that you're using which are working on emissions which are happening on the TCP stack. So now you can debug those things. So, yeah. Emit everything as much as you can, collect as much as you can, and only then you will be able to debug something tomorrow when it fails. So coming back to it, what is the need of observability? The need is just debugging and pattern detection. You know, like it doesn't really have to be failure centric as well. You can actually build patterns. Now this is important. Why pattern here? Because this pattern is something that I will carry forward into control theory. Pattern is, I see a pattern that every time request goes on to service B, it starts degrading, but on service C, it doesn't. This is a pattern. Now, if I had data being emitted, now this data could be in form of just a simple log line as well. You know, like there's a log being emitted, which what it does is request sent, total time taken was Y. Just a simple data like this, just events like this is enough. If I'm monitoring them, I know that C is the service where pressure is building. So that it helps me now take conscious decisions that if service C is degrading, I probably need to install another version of it. Now, just not for debugging something, but also for building a pattern there. This is actually a very, I've taken this from a slide by the CTO of Joint Cloud, and designing for debuggability affects true software robustness, differentiating operation failure from programmatic logic failures. Now, if you can take a moment to think what is happening here, there's a lot of information here. Operation failure should be handled. Programmatic failure should be debugged. Operation failures are, well, disk went out, network outage, CPU got full, RAM got full. These can be handled externally. Logic faults cannot be handled externally. Logic faults need to be handled by you by knowing that there is enough information that you have about there's a logic fault happening. Now to do that, you will have to actually write a software which emits so much information so that tomorrow you can debug it. Now ironically, the more the software is designed for debuggability, the lesser you will spend time debugging it. What he means by this is, and software which actually emitted every single line. Okay, so let's look at imperative code. If every register access of your code was being debugged somewhere, tomorrow when an issue happens, you directly can go to that single line that this is where the issue has happened. So a software which is designed for debuggability, when an issue happens, you don't spend any time debugging it because you already know this is exactly where the fault is. So pretty obvious thing to state, but takes a while to hit us. And the more you leverage it, it is used to debug the software around it. So let's say a bigger service calls another service, calls another service. Now if this service is perfectly debuggable, you will not spend any time debugging this. You will spend time debugging the service outside of it. Example, service A called B called C. C service has no issue at all because it's perfectly debuggable. When you look at an issue, there are logs, there are metrics where you say that, okay, service C worked beautifully. A service which was debuggable, instantly the focus is on B now. Okay, C has worked for sure. Let's spend some time debugging B. B has all the logs that you want. The issue can't be in B. Now let's spend time debugging A. So the one which is not debuggable is the one where you spend most of your time debugging. Does that make sense? Okay. Are you guys finding this a waste of your time? Okay, cool. Was it a yes? Okay. Yeah. So anyway, so the difference is, unlike monitoring, observability is not failure centric. One thing you have to understand, these are not two different topics. These are orthogonal topics. You use monitoring to make something observable. You use logging to make something observable. So it's like a superset of things. How do I make something observable? Monitoring, logging, etc., etc. These are not versus concept. This is one thing where people get a lot of confusion. So is observability monitoring 2.0? No, it's not. Observability is an adjective. It's more of this system is observable. Doesn't mean that somebody is observing it. Doesn't mean that it is being monitored. It's just observable. The day I have to, it's observable. Monitoring is that it's an act of doing something. So even linguistically, these are two different things. Yeah. Now I want to take this time to actually move towards control theory a little. How many of you actually know control theory? Like, have you studied in college control theory? It used to be in those electrical and electronic subjects. Everybody long forgotten? Okay, cool. No problem. So if you look at a software, right? The mission of a software is to give you bounded values. What I mean by bounded is the output of something should be as much predictable as possible. Let's say you wrote a function, define sum, which has two arguments, A and B. What if you couldn't predict the outcome of it? Can you rely on that software? No, right? So you have to build something where the boundary conditions are known for you. Like it moves from X till Y. What that means is, if for anything, like let's take this software consumes memory somewhere between 10 gigabytes till 100 gigabytes. It consumes CPU between X till Y. If this X and Y are not known, you can't build a software which is reliable. Like, okay, let's take it this way. You are building a login service, right? This login service may require anything from 1 MB RAM to 1 petabyte RAM. Can you build a system that way? It's not possible, right? Because suddenly the boundary conditions are outside of your control, because 1 petabyte is a different topology, 1 MB is a different topology. If I was to say this service has a footprint of, let's say the database required for this is anywhere between 5 connections to 5 billion connections. Would you be able to build a system that way? You can't. So point what we're making is, any system that you build has to operate within a bounded nature. Now, you can ignore this. This is just to make it look pretty and catch your attention. So anyway, this is just basically you add a sign function to any function and basically starts adding bounded values, but you can ignore that. Anybody wants me to explain this? I can. No? Okay, cool. Cool. So the basic premise of control theory is you give an input to a system, and most of this looks like, oh, this is electronics, this is nonsense, this is not for us. It is. Just wait for a few minutes. There's an input. Input goes to a controller. Controller is going to pass this input to a system, which is going to yield an output. A lot of you will not associate with this, right? Let me catch your attention and let's associate with this. Let's make this system our API. Let's make this controller our load balancer. Let's make this input and this dot a mobile phone. Does this make sense now? Instagram, load balancer, mobile phone. TikTok, load balancer, mobile phone. Do we associate now? Okay, good. So now in this system, we have to add bounded nature to it, right? What we are trying to say is the behavior of this is we are going to control this. So let's say a request came in and output came out. Now, what if we started measuring the output and started capturing it somewhere else? What we're trying to say is load balancer sends a request to something, to your TikTok video or your Instagram upload. First time it takes 10 milliseconds to upload. Next time, again, we could be observing any attribute of a system. The assumption is system is observable, right? So right now I'm going to start observing the latency. 10 milliseconds when it goes to server A. 20 milliseconds when it goes to server B. And there is a pattern. Now suddenly I realize that every time there is request reaching server A, it works between 0 to 10 milliseconds. But when it goes to server B, it takes somewhere between 20 to 100 milliseconds. Just data being recorded. We're not taking any decision yet. We start capturing those data points. Now, what sort of decisions can I take on top of this? If I start feeding this back into my load balancer, somehow I can start taking decisions like do not hit server B at all, because it is going to result in a degraded performance. These are decisions I can take. I'm not saying I have to take. This is now tools and levers that are with you to allow you to write better software. Now you would say, how would I do that? I mean, that's a different concept altogether. There's another talk which I did, which is about load balancing techniques. You can watch that. Over here itself, you can now connect to a different endpoint itself. Now, how would you say that? But you said this is my mobile phone. How would my mobile phone take that decision? DNS takes that decision for you. Every time you go on AWS, Route 53, you remember there is weighted balancing there? Ever wondered what it is? It is something like this happening there at the back. So your mobile phone makes a DNS query because it has to connect to the API endpoint. The DNS that it resolves, there's an IP address that it's going to return. That IP address is taking into account your load or other such statistics, and it is always going to give you the best one. So this ability of having data being recorded or making it observable starts allowing you to make better decisions and start writing better software. Now this is already happening in 100 other places. You may never know of it. Like DNS is one example I gave you. I'm going to give you another example very shortly. Are you guys able to associate with this better? Okay. I'm going to take a slightly complicated example. Have you guys heard of Envoy? and ever wondered what these things do? Envoy, Kubernetes, is that making sense now? Okay. Now you have, so what they do, anybody heard the word Hystrix as well? Yeah, cool. So Hystrix is, for those who don't know, who doesn't know? I'll just quickly explain. A minute more. Cool, fantastic. So we'll just spend half a minute on this. It's a set of utilities which were released by Netflix. So you can think of these as design principles, but then also coded into an available as library. You know, like as Java first, then Golang also did it. Python may also have it, PyHystrix. What this does is it's a collection of good practices. What they do is they do things like back off on a failure. You know, like if there's a failure of a request. Okay, so how many of you write APIs here? Okay, has anybody integrated with a third-party payment service? Or any third-party service? Has anybody ever made a request call, request.get, request.post? You guys have, good. We have to get down to a point where everybody agrees with it, right? Now, when you do a request.post, if you get a failure, what do you do in your code? No, like imperatively, I want you to tell me, right? You're writing x equal to JSON body, in your way x equal to JSON body, request.post JSON body. If this line gets an error, what do? Try accept, what happens in accept?
Relog and retry maybe, or
fantastic, retry. See, there's a decision that you're making, that I'm going to retry this. Now, this is already, you guys are doing this on daily basis, right? Now, this retry, how long do you wait for a retry? Do you retry instantly? Do you retry after a while? How does it happen? Now, these are decisions that you'll have to make, right? Now, so there are these algorithms here, you say back off. What you say is that if the first retry did not work, it's not going to automatically fix. So wait for a while, do 1, 2, 4, 8, go any sort of algorithm. Now, this is one such principle. Another such pattern that they use is circuit breaking. What circuit breaking does is, if a domain failure has happened, now this happens in a slightly convoluted architecture. Let's say you are Amazon scale or something which is pretty, I'm sure Flipkart guys also do it. You realize that a certain route path, a domain or an endpoint is failing. It's going to fail for everybody. Every person on that, let's say an example, alphapay.com, I'm going to not use any real name here, but say any XYZ payment service, let's call it Alphapay, has gone down. Every user on your website is not going to magically work. It's going to fail for everybody. Now, imagine there is a Diwali sale going on. You suddenly realize that the payment service has gone down. You can throw an error, you can keep retrying. It's not going to solve the error, right? So retries didn't solve it. What do we do next? Now, should we have this retrial go for all the million users and transactions happening on the website right now? It's not going to solve anything, right? What you could do alternatively is, when you realize that a certain critical mass has failed, what you do is you cut this off. That this domain, we're not going to try at all. I'm not going to try a payment at all right now. Let's process all orders and let's do payments asynchronously. This is a decision that you could take as well. Suddenly you're moved from a synchronous to a queue-based, that, okay, process everything, fulfillment will happen later, because you want a better user experience. So these things allow you to build such flows where the perception of your software will become more reliable as well. And that's exactly what you want to do, right? Because this is not just about technology, it's about business as well, where it sees a product to be reliable. Make sense so far? Cool. So I'm going to take example now of, how many of you know TCP flow control as an algorithm? Okay, you can take a nap. Others, do you want me to explain quickly what a TCP control works? Because this is one of the beautiful examples of control theory in practice, which is being used for almost 20 and 30 odd years now. And we just haven't paid attention to it. So how TCP flow control works is, so from A to B, data has to be transferred. There are X number of bytes that need to be transferred. Bytes we will take a MTU size and we will split it into packets. So at any point, if you are not with me or you lose me, just raise your hand, right? It's okay, silently raise the hand. The ones at the back, front, the people in front can't see you. Okay? So let's say there is 45,000 bytes to be transferred, right? Now each packet size will take it as 1500, all right? So how many packets need to be transferred? 30, cool? Now in a single, so total file, let's say there are 300 packets. The first thing that happens in TCP, when A establishes a connection, this is ACK, SYN, etc., all that history done. After that, there is a window size which is transmitted. The window size is on the side of the receiver, there is a TCP buffer before application can read from it. Are you guys aware of this part? Okay, if you're not, on the consumer side of a TCP connection as well, the receiver side, in memory buffers are created before an application reads from it. So when you do request.get, underlying there is a connection which has a socket and you do a sock.read. That socket.read buffer is actually reading from this buffer which has already been received from another service, right? From the other side of the pipe. Imagine it as a pipe, I pour water in it, I run the tap out, but before I run the tap out, water is still collected on this side, right? It's as simple as that. Now, in flight it says, I have a buffer on my side of 30 packets. You can translate 45,000 to 30 packets now, fair enough, because 1500 is the packet size that we're taking. So B says I can accept 30 packets in my buffer before my application, Python, Golang, Java, .NET, doesn't matter, reads it because it's just TCP socket. It's language agnostic. A realizes I can send 30 packets. It transmits 30 packets. When it transmits 30 packets, B sends an acknowledgement of 10. That 10 have been received. Now when 10 have been received, in the entirety of 300 packets, I still had more packets to be sent. Now A has to send more packets. Now when A has to send more packets, there 20 remain, it sends 10 packets. Why? Because only 10 were acknowledged and the buffer size was kept as 45,000, right? So which is 30 packet is the buffer window which is max that it can accept. 30 is done. Now the next time, the application, Python application has become slow. It's doing some time.sleep or something, writing a database where it is not able to read from the buffer yet. When it receives it, it says, and it returns a window of 30,000. That the buffer is 30,000. Now A cannot send anymore because there are 20 packets already in flight, which is 30,000 bytes. It can't send any further. So A won't send any further. Now when A doesn't send any further, after a while, B sends another acknowledgement of I have accepted 10 more packets, but my application is still sluggish, so the receiver window is 0. A cannot send anymore because there is no room left to be sent. But what this means is this would result in a dead connection. So A after a while will send a probe as well. Now all of this is actually baked into TCP for past 20 years. And this is exactly what control theory is, right? Every time there is a feedback being received by your system underneath of everyday code that you write. The Python code that you write every single day, the .NET code that you write, the Java code that you write, this is happening. There's a control feedback. This feedback helps you to write reliable software, better software. And this is how TCP reliably sends data. Fair enough on this? Cool. Now we're going to look at another aspect of TCP, congestion control. TCP is itself an amazing protocol. Like you can actually just read it and understand so much out of it. So what TCP congestion control does is, flow control ensured that we are never going to send data which is more than the receiver's ability. Congestion control takes it one step further. what it also takes into account is network failures. Now, what it does is, every time TCP starts a connection, the first thing that it does is, it only sends, no, that's just timing for me, 10 minutes left. It sends fewer packets. What it's not going to do is, if there's 1 gigabyte to be transferred, and there's an MTO 1500, let's say you can only send X packet, it's not going to try and transmit entire gigabyte. Because it has ability to retry, it's not going to sit and choke your pipe. Like, okay, let's keep retrying gigabyte every time. That's not how it works. What it does is, it first sends a packet. You get an acknowledgement. Then it tries to send 2 packets. Then it gets 2 acknowledgements. Then it tries to send 3 packets. It gets 3 acknowledgements. And this 1, 2 becomes 1, 2, 4, 8, 16. There's an exponential growth that starts happening of trusting the other side. This is called slow start. So every TCP connection first starts with a slow start. Then at a certain tipping point, it realizes that, okay, this exponential cannot be sustained because networks are unstable. Like, next time when you write application, I want you just to remember this. Even if you don't believe me, trust me, one day you will. Networks are going to be unstable. There's no network which is stable. And TCP works on the same assumption. So after a certain tipping point, it moves into linear focus. That let's not do exponential now, let's linearly grow till the first acknowledgement doesn't arrive in a given time frame. So if it accepts if it expects that acknowledgement would be back with me in 10 milliseconds, if it doesn't happen, it marks it as a failure. Even a failure, it drops down the rate by 50%. Subsequent 2-3 failures, it will fall back to the slow start. And then TCP will start again. So if you ever wondered, I'm assuming everybody has done torrents, right? Like what is rule number 1 of torrents? The more you watch it, the slower it gets, right? So anyway, so if you would have realized, like many a times what happens is you're trying to download a file or you're trying to initiate a TCP connection and you realize that it's behaving weirdly, like what you can do is simply check in your ping as well if you see packet drops. Because every time there's a packet drop, your connection comes back to the slow start. So the burst of packet transfer that was happening, it's going to stop. It will again re-establish the connection. So flaky connection is actually is worse than no connection. Because what you're trying to see is that, oh, I got a 16 Mbps bandwidth. But because it's dropping packets in a while, it is as good as having a few kbps of connection. Because it's always going to start again. Like 2 subsequent failures, it falls back again. I mean, all of this can be changed. There are a bunch of, there's cubic, there are too many protocol implementation and you can change these as well. But I know default system, this is how everybody uses it. I'm going to now take practical applications. You're like, okay, a lot of this feels like theory. Like why should I be using this? Why should I even care about this? So practical applications are constrained optimized problems. Why do we need control theory or any such system to be implemented? And I don't want you to look at it as a complicated thing. You're like, oh, it's control theory. No, it's just a feedback loop. You're doing something, you're recording the data, and you may decide to act on that data. One is constrained optimization problem. Given a set of constraints, how can I reliably deliver better? Exactly how TCP does. Constraint scaling problem. Once you have realized that there is a feedback coming in, that this is not enough, you have to change the constraint itself. Example, constraint scale problem, auto scaling, right? That's an auto, that's a scale. So you get a feedback, right? That, hey, RAM is not sufficient, CPU is not sufficient, let's scale it, right? This is a feedback loop, right? Everybody knows this concept of auto scaling in Kubernetes, AWS, right? This is what's happening. You have data which is constantly coming in, you keep monitoring it, you have certain set of rules, and using those rules, you change it. But you can't just keep expanding it, you have to shrink it as well at some point of time. So this dynamic up and down is just a feedback loop cycle. Cache. Now, when you use a cache, right, in your system, you use databases, right? Like complex databases, Cassandra, then you use Aerospike DB, blah, blah, etc. Disk cache as well, SSDs, all that, right? All of them underneath, intelligently, what they're trying to do is, whatever you access faster, just 2 minutes more, whatever you access more often would be automatically cached. Now this is where those all algorithms come in, least recently used, most frequently used, blah, blah, etc., right? All of this. So every time when you're building these caching systems, you are using a feedback loop and use it. Gateway, load balancers. When DDoS happens, when Cloudflare comes and tells you that, hey, we're going to prevent DDoS for you, what are they doing? They're just using a feedback loop mechanism underneath, that every time there is some request coming in, there's an IP address. What they see is that, oh, this is where the request burst is coming from. This is increasing my throughput. This is where I see a pattern, and let's block this. There's a certain action that they would take. Load balancers. Load balancers use this as well all the time, because the concept of load balancer assume there is a definition of load. Load cannot be defined by the sender. It has to be defined by the receiver. It's a feedback loop that the receiver tells you, this is my current load, don't send any further, back off, don't give me any more. Logstash is being built on this as well. Why? On Elastic ELK stack, when you send in logs from file beat, Logstash tells, hey, back off, don't send me more files, file beat. That's another feedback loop cycle. Lastly, progressive streaming. Everybody watches Netflix, right? Have you realized it doesn't stop? Like, no matter how bad internet you may be on, like, Telegram won't connect, WhatsApp won't connect, but Netflix keeps working. Progressive streaming, right? What they're doing is, on every single packet transfer, every adaptive next transfer, the bandwidth is being reported. That X bytes were sent first in Y milliseconds. Now it is being sent in 2Y milliseconds. So bandwidth is fluctuating. So drop the bandwidth at which you're sending, which is progressive streaming. What is happening is, first it was sending. So have you seen that when you watch a video, it says auto bandwidth? Now that's exactly the start. It's going to adapt itself. Cool. Last converging thought, software by default is opaque. To debug and control a running system, you need observability and observation built in. Thank you. I'm Piyush Verma. And yeah, that's it.